Hello, we have done our research on 6 papers for hardware protection, and this is a combined PPT on topic watermarking for hardware protection. Now let me introduce to our main topic. Protecting the IPs deployed in modern SoCs have become more difficult as the IP houses have been established across the globe over the past 3 decades. The threat possessed by IP privacy and overuse has been a topic of research for the last decade or so and has led to creation of a field called watermarking. IP watermarking aims to detect it by embedding non-functionality circuit into the SoC. IP blocks are delivered in three main categories depending upon the price application. It can be mainly categorized into three divisions. The first is soft IP, then it's the firm IP, then it's hard IP. Soft IPs are basically delivered in the form of synthesizable hardware design language code, that is the HDL code. And unlike soft IPs, the hard IPs are optimized for a specific technology and are typically mapped to a particular semiconductor manufacturing process. And a firm IP is a specialized design component used in creating electronic devices, and it falls between the flexibility of the soft IPs and the specificity of the hard IPs.
As we can see, the watermark insertion during different stages of hardware design, that is, they are divided into three categories: higher, mid, and lower extraction level. So the general requirements of IP watermarking are credibility, low overhead, resiliency, invisibility, and granularity. Uh, Credibility ensures the trustworthiness and authenticity of the embedded watermark in hardware IP. Low overhead is vital, minimizing impact on performance and ensuring efficient operations alongside robust protection. Resiliency or robustness is a key requirement, ensuring the hardware watermark can withstand various attacks and maintain its integrity. Invisibility emphasizes the need of the watermark to remain imperceptible, working silently without disrupting normal hardware functions. Granularity determines the level of detail in the watermarking process, striking a balance between effective protection and minimal interference. Also, my watermark should be resistant to these some attacks, that is tampering, forging, and reverse engineering. So, tampering attacks basically involve unauthorized alterations to the embedded watermark in hardware. Forging attempt to create counterfeit watermarks, posing a threat to the authenticity of intellectual property. And reverse engineering, basically it is attack target deciphering the watermarking algorithm, potentially compromising the security of the hardware IP. So IP can be of three types, as we discussed earlier. Uh, so an efficient way for soft IP protection is discussed here. So several soft IP protection methods by watermarking HDL source code, including module watermarking, modules duplication, and module splitting, uh, were already developed, but these methods implementation cost is too high. So a new watermarking method of additional circuit based is proposed for soft IP core protection, in which a watermarking module is added in the original circuit to prove the ownership rights of the IP provider. The additional module can switch between two working modes: normal operating mode and watermark generating mode. So yes, in traditional additional circuit based watermarking methods, the watermark generating circuit is separated from the original circuit. This greatly increases the risk of being attacked. So in this method, the additional block is functionally integrated with the original circuit, so that the ability of resistance to tampering attack is enhanced. The additional circuit can work in two modes: normal operating mode and watermarking generating mode. In normal operating mode, the output information is selected register data which involved in the arithmetic of the primary circuit. It makes the watermark module can't be removed directly. The ownership rights can be checked according to the output sequence of the additional module working in the watermark generating mode. The other two methods are hiding watermark in storing device and embedding watermarks in separating circuits are compared, and we have done an analysis uh, as given in this table. So from the results, it can be seen that our proposed method has only 3.0 0.04% more hardware overhead, and it is acceptable for designers. So the power consumption at the delay and F max keep the same level for three all these three methods. Moreover, while the watermark in other two methods can be easily removed, this watermarking approach has better robustness.
We have studied three research papers from the current year to explore the novel ideas of watermarking for hardware protection. Some of the novel ideas are beginning with the PSC watermark, power side channel based IP watermarking. It uses clock gates. It embeds a power signature with very minimal modification to the IP core. It is done by reusing the existing clock gates to modify the dynamic power consumption inside the IP. It generates a unique power trace that works as a signature of the IP. So here, clock gating is used in PSC watermarking. Clock gating is a power optimization method that reduces dynamic power by restraining transitions from propagating to the inactive segments of the design, such as registers, clock networks, and logic. It reduces dynamic power because the clock has a high activity factor, and the switching activity of the gated registers become restrained, which turns off large uh, logic blocks. In the diagram, we can see the programmable ICG cells, regular and programmable ICG cells, and we're getting G clock. Next is the framework of the power side channel based watermarking. The orange boxes are the additional steps required by the PSC watermark for signature generation, and the green boxes are for detection. So the results that we got from the PSC watermark were, upon evaluating the technique on several benchmarks of varying size, that is MIPS Open MSP 430, in the presence of multiple non-watermarked cores operating in parallel, it obtained greater than 90% confidence rate in providing the ownership of each watermarked IP core. The IP cores are watermarked in a subtle and obfuscated way with less than 4% overhead, which makes the proposed technique hard to detect and remove or modify. Next, the conclusions of the PSC watermark are that this novel idea uses programmable clock gates that offers multiple advantages. It can easily be detected using a power side channel analysis that does not require physical access to the IP. It does not alter the original functionality of the IP core and has a low hardware cost and is robust in terms of applicability. So we have evaluated that the tampering or removal of the watermark power signal is very difficult due to its well hidden nature in the IP design. Next novel idea is the FPGA core watermarking based on power signature analysis. This is one of its kind. It is a new method to watermark FPGA cores where the signature is detected at the power supply pins of the FPGA. So with Xilinx FPGAs, we can integrate the watermarking algorithms and the signatures into the functionality of the watermarked core. Thus, it gets very hard to remove the watermark without destroying the core. Here, we introduce a detection algorithm which can decode the signature from a voltage trace with high probability, and then a second algorithm is introduced which improves the detection probability in case of considerable noise sources. Now, this is the diagram for FPGA. We are probing at the voltage pins. The problem of watermarking FPGAs is not the coding and insertion of watermark, it's the verification with an FPGA embedded in the system. Now, concluding the watermarking FPGA, we have presented a watermark technique for FPGA cores where the signature is easily extracted over the power pins of the FPGA. It is hard to remove the watermark, and only very few additional resources were required for control. We described the detection algorithms, and experimental results showed that the functionality of core is not altered and that it is possible to detect the signature over the power trace of the FPGA. Also, the experimental results have shown that decoding is not possible in all cases, but we can improve the quality of results. Next up, moving up to a new novel idea. So, FSM inspired unconventional hardware watermark using field assisted SOT MTGA. This novel method is used for creating hardware watermarks inspired by finite state machines. It makes use of unique physical property of magnetic tunnel junctions (MTJ) that are based on spin orbit torque (SOT). This design strategy takes advantage of unique switching properties of MTGA, their non-volatility, and their reliance on external magnetic field to direct information through a predetermined order of states in FSM. So here is the block diagram of the proposed watermark generation on the left, and on the right we have the algorithm of proof of ownership. So coming to the results of SM inspired unconventional hardware watermark. So this performance prospects were analyzed using Monte Carlo simulations for the 5% and 10% of process variation in the key MTJ parameters. The accuracy of 100% and 99.8% were achieved. In control signal voltage variation, a tolerance of 9% is observed. The required state transition is not altered, demonstrating a tolerable sensitivity to temperature variation from 250 K to 350 K. The security aspects and methodology for the approach are explained to ensure a more robust and practical application. And now comparing this particular result with the other FSM based watermarks. So this is the comparison. Here we can see that for our work, the overhead is high, invisibility is low. So concluding with this technique uses an external magnetic field to guide the MTJ in an actual IP core properly and inserting the MTJ block with other CMOS devices in the SoC design. This is complex. By utilizing this compact model in EDA tools, this work offers a potential future use for hardware watermarks. Monte Carlo simulations are performed to show the robustness to the device imperfections. Thank you.